All right, hi, my name is Mueller. I'm going to present some work that we did on forecasting network intrusions using data from security logs. And this was work done with my colleagues from Leidos, Alex Memory and Kyle Bartrem. So just a little bit of background. This is a continuation of some research that we did as part of the IARPA cause program. And if you're not familiar with IARPA cause, the goal of the program was to develop and test new automated methods that could forecast and detect cyber attacks significantly earlier than existing methods. And as part of the IARPA program, our as part of the cause program, we were provided data from a large anonymous organization, and we were able to define queries using the organization's security information and event management system. And for this work, we used two sources of data. One was the network security logs produced by Zeek, and Zeek was previously called Bro, and it's this open source network security platform that transforms the network traffic into high level events and network intrusions detected by the IDS system Suricata. And so here's a description of the network traffic data that was collected. So we had things like inbound and outbound connection ports, internal connection ports, MIME type and directions, so inbound and outbound file types, paired FTP command reply codes, and Zeek also records these kind of weird events which do not conform to standard protocols, and we recorded these weird events by their source IP address, but we only looked at the first byte of the IP address. And for the network intrusion data from Suricata, we had quite a few different types of intrusions. So things like web application attacks, things like code injection, cross scripting, other things like DNS spoofing attempts, if there was a Trojan detected on the network, other things like privacy violations and privilege escalation attempts. And I should say these are all hourly counts of these events. We didn't have access to the timing of the individual events, but rather just a hourly aggregation of each type of network intrusion. And these were categorized by different risk levels. And here you can see just a small plot of the total number of alerts by risk level. And here's just an overall picture of the data. So the data was collected over a period of 2 years. And you can see this is kind of like a temporal heat map where there are several periods of missing data. And for this reason, we chose a subset of the data to look at. And this resulted in around 6,000 observations for 325 different variables. We also did some pre-processing of the data. We removed all the variables with a very low variance. And this resulted in 113 different network traffic variables and 18 IDS alerts. And so for our forecasting problem, we're interested in forecasting future values of these IDS alerts. So things like how many network Trojans will be detected in the next 12 hours, basically, an hour by hour forecast. And we use the past values of the given IDS alert plus the network traffic data to try to forecast these. But we want to compare that to a couple baselines. One being a naive baseline where the forecast is just set to the last known observation. And a REMA model, we also used it as a baseline, and this would be a scenario where the network traffic data, which is we consider to be exogenous, is not useful in forecasting. And we chose the parameters for each ARIMA model using kind of an automated process described by Hinman and Kandekar. For our main forecasting model, we use just a LSTM, recurrent neural network. The input for the neural network was this set of all the network traffic data plus the past values of the IDS alert that we were interested in forecasting. And we used a lag of 1 week. So 168 hours in the past were used as input, and we wanted to use that to predict 12 hours into the future. And this is the architecture that we used for each of the LSTM model. And to train the model, we sliced the data up into subsequences where each input was, as I mentioned, 168 observations in the past, and then we used that data to forecast 12 hours into the future. And we ended up with around 4,000 of these subsequences to train the model on. So here's the results. We recorded the mean absolute error. This is a time series regression, so that's why we chose that metric. And you can see for some of the IDS alerts, the naive model performed best. Others, the ARIMA was best, but in general, for most, the best performing model was the LSTM. And here we'll kind of discuss a little bit of these results. In cases where the naive baseline worked best, the data was pretty sparse, so you can see some of these IDS alerts where the naive worked best on the right-hand side. You can see these, in general, they were kind of like bursty events, and then you didn't see any activity for a long time. Or they had pretty low variance, but still enough variance to be considered. And on the left-hand side, you can see kind of an example forecast of the LSTM model. So you can see it, forecasted reasonably well. And then as you got further out in the forecast, the error kind of increased. But in general, we were also interested in actually what the LSTM, what kind of insight you could get from the learned models where the network traffic data was useful in forecasting the future. So one of the things we did were to look at the values of the gradients of the output with respect to the input values. And this is a common technique in explainable AI. So it's kind of known as a saliency map, and it looks at, which kind of, in the image domain, which pixels are the most important for determining the output of the neural network. So when we did this, we can look at the gradients across both time and the input time series. And one of the things that we noticed was the gradient values quickly dropped to 0 beyond 24 hours. And this pattern holds across all the IDS alerts that we examined. So only the very recent past was useful in forecasting the future. And we can use the same technique to determine the most important network traffic features for predicting the future IDS alerts values. So in this case, we would just average the gradients across time and then sort by the absolute value of the average gradient. So here's just an example of kind of ranking these time series by gradient. And here's a table with a detailed description of those, the top two features. So here, there's a couple of interesting things I think that you could kind of look at. For example, potential corporate privacy violation. The most important features were outbound audio files and inbound Chrome extensions. So that kind of tells me that, maybe this corporation wanted to restrict sending out audio files, and some Chrome extensions were not allowed by the security team. So again, these are kind of interesting ways to kind of gain a little bit more insight into what the models thought was important. So this is quick, but in conclusion, some IDS alerts can be accurately forecasted up to 12 hours ahead, and for not all, but some of them, for most of the IDS alerts that we looked at, the network traffic data was actually useful to the forecasting models. And also only the near past is useful in forecasting anything into the near future. And when we look at the gradients of this LSTM network, it may help you kind of gain some insight into what these alerts are actually, what kind of network traffic is driving these alerts. And these models might be useful in developing some kind of a forecasting application which would help SOC analysts understand what level of alerts are expected versus if there's something unusual going on. Thanks.